Hello everyone, welcome to the class. I am Dr. J. Jayakumar, Assistant Professor in Xavier's College, Palankote. This is a organic chemistry course. However, it's a extra credit course. Therefore, in organic chemistry, this particular module will focus on biomolecules and its significance. The course code is 23 PCHE31. So, biomolecule. The molecules, organic molecules especially, that are very essential for the living system in terms of supporting the life and other metabolic process are said to be biomolecules. We do have various biomolecules, example protein, amino acids together gives rise to protein. Apart from proteins, we have vitamins and we have various other biomolecules. But then this particular video focuses on the carbohydrates and the proteins. And then in course of time, we'll be looking into the other biomolecules that are present in it, present in the biological system. We go into the biomolecule in general overview. The biomolecules are the fundamental components, as I said earlier, and they are very important for essential life. For the normal metabolic process, every higher mammals or even smaller reptiles and other living system also requires biomolecules. So where exactly they do really require? Where do they really require? They require in diverse structures for the growth and for a storage of energy. Even they present in the membranes to carry out the different activities and for signaling purposes. All these purposes we are wanting the biological molecules. And we start with the amino acids. As I told, proteins together is a bulk unit. However, the proteins are formed by the basic fundamental unit called amino acids. What is amino acid? The organic molecule that contains amine as well as carboxylic group together forms amino acids. And amino acids are essential for various purposes like to build protein, or otherwise they will fold into three-dimensional thing, that is they will do some exact biological function. Say they will, in terms of DNA, they transport information or hormone. All these functions are mainly inclined to the amino acids and proteins. They also support for catalytic activity and so on and so forth. Now these is a somewhat outline. I can read it for you. See, carbohydrates, of course, it is an energy house. Lipids, that will store energy inside the cell membrane as well as it is used in signaling molecules. Proteins, catalysis, immune function, transport, so on and so forth. Enzymes, they do execute biological reactions and very essential for various metabolic pathways. Minerals, though it present in trace quantity, still it is also very important for health and hemostasis. Thank you.
Usually, when kept in an UV spectrophotometer, it will absorb light at some particular wavelength. The region where it shows the larger absorption is called a chromophore, meaning chromophore would be a part of the protein that absorb in a larger scale, meaning it may dominate the spectrum. That is called a chromophore. Therefore, while you examining the UV spectrum of a biopolymer, usually the chromophore will absorb light lesser than 300 nanometer. That's the first information one should derive. But but the point is, solvent also plays a very crucial role in determining the UV absorption. And therefore, what solvent to be taken to study the polymer in an UV spectrum photometer? The solvent usually preferred is water. Why is it so? Because of having greater solubility and the pH is around 7. These two factors make the water as a dominant solvent to study the protein for a UV spectrum. But the same water also comes with some limitations, meaning it lay restriction in absorption. It hold the free absorption of the protein. Why it arrest some absorption or alter the absorption pattern? It is because due to the solvent-solvent interaction or maybe solute-solvent interactions, or it is being a polar solvent, it may contribute for the dipole effects. Because of these things, sometimes the real structures of the protein may to some extent hampered or affected by the solvent, exclusively water. Having given that idea, we can now inspect the a protein in an UV spectrum. In an UV spectrum, the UV region itself can be classified into two. One is far UV region, which spans between around 190 nanometer to 230 or 240 nanometer. The other region would be near UV region, which is around 230 to 240 to 300 or 340 nanometer. So I repeat, far UV region spans between 190 to 230, and near UV regions comes after it, that is at 240 to 340 region. So these are the two important regions present in the UV. I mean, now how to go further? We can now understand the chromophore by three ways. Assuming the chromophore as a peptide bond itself, or considering the amino acid side chain residue, or the prosthetic group. These are the three important groups which are attributed for a chromophore, which show a significant absorption in the UV spectrum. Let's focus our attention towards a peptide bond. In peptide bond, so what is a peptide? A peptide is this. Okay, this is the peptide. That is the carboxylic group OH and the amine group of another protein fuses or condenses such that water is eliminated, and there which there is a bond, new bond formation. This bond is called peptide bond. So this is why the peptide bond. In the peptide bond, the chromophore or otherwise the absorption mainly takes place between the electrons resides on the oxygen. Okay, if it is a formaldehyde, we can clearly tell that the electron, the lone pair of electrons always associate with oxygen, which shows a strong pi to pi star pi to pi star absorption. But as far as amide is concerned, there is a possibility of the delocalization of electron. Because of this delocalization of electrons, the electron may not picture or may not present exclusively on the oxygen, but it will be spread all over the ring, meaning it spreads across carbon, nitrogen, oxygen. Which carbon? This carbon. See, oxygen, carbon, and nitrogen. In the three atoms, this electron will spread. When it spread, and that leads to a weak interaction with and that is attributed for n to pi star transitions, and it shows very weak intensity, probably epsilon max, that is intensity would be around only 100. Okay, so it undergoes a weak transition. That's why usually at the region between 190 to 230, we can expect for a band. If at all, if there is any band, that band should be caused by the peptide group. That's the idea that one can derive just by inspecting the UV spectrum. Okay, we have an example. This is a UV spectrum of poly L lysine. This is dissolved in water, so we are taken aqueous solutions. It is having various structural features. Probably in one end it acts as a coil, in the other end it acts as a beta sheets. So it is exist in two structural features depending on the pH and as well as the temperature change. No matter whichever the structure it stays, it shows the absorption at this range, right? So this is attributed for the n to pi star transition, and that clearly assigned for the presence of peptide-peptide bond. That's what justifies. The peptide group usually dominate at the far UV region, and that has been proved over here. So while you inspecting a protein in an UV spectra, if you find any absorption near at 190, for sure we can confirm the presence of peptide group, that too in the far UV region. Okay, going for another typical example, mystery amide. This is the mystery amide. In the mystery amide, usually the pi electron should be present on the oxygen, as well as there is must be a lone perf electron to be present in the nitrogen. But realistically, it is not happening. What really happens is this lone pair electron circulates on these three ends. Okay, so this electronic transitions can be movement of this electrons can be noted by the transition dipole, and this transition dipole occurs to the plane bisecting or near to this group, and that is why rather than the expected pi to pi star transition, okay, the expected is pi to pi star transition because the electron has to be on nitrogen as well as on the oxygen. If they stays in the oxygen and nitrogen alone, you will be expecting a pi to pi star transition. But unfortunately, the electron delocalizes. Because the electron delocalizes, pi to pi star transition did not happen. It is forbidden. What really happened is n to pi star is happened. Maybe at higher concentration or at higher energy, this even changes from n to sigma star. Okay, so this is what really happened. So this clearly tells that at far UV region, the peptide dominates the spectrum. Thank you very much. Okay, now we go for the other addition. The problem of detecting the amino acid is this. When amino acids or the proteins, when expecting for a UV spectrophotometer, there will be lots of absorption. We know that from the previous episode, that the absorbance will be very broader because of the use of the salt. That is on one hand. The other problem is when the amino acid have a side chains. Example, look into this amino acids. Aspartic acid, glutamic acid, histidine, glutamine. They do have a longer side chains. All these side chains will give absorption, but they do so in the same absorption region, and therefore detecting is becomes very problem. Okay, as I told earlier, the same transitions happens at the similar region, and therefore how to move forward? It's better to inspect their absorption after 230, and that's how we go into the near UV region. The near UV region spans between 230 to 340 nanometer. In this region, one can usually look for the chromophore. Example, the aromatic rings. How do they show absorptions? And these may seems as an asset in detecting the presence of the particular amino acid group. Example, we consider the three amino acids neutral pH. For example, tryptophan, tyrosine, and phenylalanine. They, in the near UV region, shows peak. Example, phenylalanine shows a weak intense band at 250 nanometer, whereas the tyrosine shown similar, maybe at 274 they shown a band. Okay, but then it is fairly intense, whereas tryptophan, it gives nearly three peaks. Maybe it appears to be shoulder, but then between 240 to 290 it shows, give me a minute, 240 to 290 it shows nearly three peaks, and it is very intense. So what they tell you, it clearly tells that the presence of the aromatic groups, or in case of tryptophan, it is the indole ring, shows a greater peak, and therefore in the near UV region, it is the aromatic acids shows the characteristics band, or otherwise it dominates the region, therefore it will fetch some useful information. Now, does a pH any role to play with? Realistically speaking, the pH has a very little effect in the absorption spectrum in the given region, that is in the near UV region. However, the same is not observed for tyrosine. As far as tyrosine is concerned, when taking when analyzed at various pH, probably 12 to 11.5, there is a shift, drastic shift being observed in the absorption. Why is it so? It's because of the presence of the OH group, the proton, hydroxyl proton. Upon removal, the shift has been taken place in the band. So, and as a whole, one can understand that at the far UV region, it is the peptide that will give significant information about the protein. But after a far region, that is near UV region, 230 to 330 nanometer, it is the aromatic acid which can give up some useful information in understanding the real protein or amino acid residue. However, caution must be taken because the excess of presence of side chains obviously complicate the spectrum. Thank you very much.